my name is McManus. As it says here, I'm on the physics product management team for the Simcenter STAR-CCM Plus CFD tool, and part of my role for the last few years has been focused on how we can leverage the power of GPUs with Simcenter STAR-CCM Plus to really accelerate CFD applications, and that's what I'll be talking about today. So what I'll cover, I'll give a brief overview of Simcenter STAR-CCM Plus if you're not aware of the tool. I'll also cover a little bit on GPUs, why now, why are they really coming to the forefront with regards to CAE and HPC type applications. I'll then give some specific details on the Simcenter STAR-CCM Plus approach to GPU acceleration, and then I'll also give some more practical advice on how to get up and running with GPUs, and also a specific case study. Thanks to the team at VSC for giving me access. I'll show some numbers on our Aero SUV automotive aerodynamics simulation, which we were able to run on the Hortense Tier 1 supercomputer. And then to wrap up, I'll just give some final thoughts, what we see looking forward with respect to GPUs and CFD with Simcenter STAR-CCM Plus. Okay, so what actually is Simcenter STAR-CCM Plus? Hopefully you've heard of it before, but if not, then as it says here, STAR-CCM Plus is a multi-physics computational fluid dynamics software for the simulation of products under real-world conditions. So this is a very high-end example here. You can see this helicopter rotor type application, a lot of different physics going on there. We have the aerodynamics, the rigid body motion and the morphing of the helicopter blades, lots of different things going on there. And STAR-CCM Plus is a tool that can capture all of that type of high fidelity and all that multi-physics. I think we'll see two industrial examples with the presentations after me, kind of highlighting the wide range of applications that can be undertaken with the software. Likewise, it's primarily a CFD tool, but the idea here is it's a fully integrated software set. So that means all the way from your CAD right through to post-processing can all be achieved directly inside the STAR-CCM Plus tool. And likewise, we can basically run design exploration as well built into the software. So really good tool set. I've been lucky enough to use it for I was 5 years as an application engineer and continued for the last 3 years in the product management organization. It's really an excellent range of things that can be undertaken with the tool set. So during the presentation, I may make reference to different versions of the software. So just to clarify the versioning, so Simcenter STAR-CCM Plus is released 3 times a year, and we typically number it based on the month and then the year of release. So we just recently had our 2402 release in February, and coming up on the horizon will be our next release in the summer, the 2406, and then in October our 2410 release as well. So yeah, there's a fairly standard release cadence every 4 months where we add more and more functionality to Simcenter STAR-CCM Plus. So with that out of the way, then we can focus a bit more on the specifics today of GPU-accelerated CFD. And something I do get asked quite often is why now? I think it's clear there's been a very big trend towards leveraging GPU hardware over the last few years, certainly from academic codes all the way through to commercial CFD codes. Most of these are now offering GPU solutions or the ability to leverage GPU hardware. So there's a few drivers for this, specifically from the STAR-CCM Plus side of things. Then our objective is to maximize the use of all available compute power that our customers are interested in using, and GPUs are becoming an increasing proportion of this. So I'll show the breakdown of the Hortense compute nodes, and you'll be able to see that already, which is really nice, that VSC have GPU compute nodes available there. And that's a general trend that we see not just in supercomputers, but across any kind of HPC installations that are looking at computer-aided engineering type applications. For the GPUs themselves, then there's been really nice performance improvements over the last 5 to 10 years. So the introductions of high bandwidth memory really make things a lot more suited for unstructured CFD computations. And you can see from the plots here that the GPUs are really potentially pulling away from CPUs with respect to that performance benefit. So we expect to see continued improvements with regards to the performance metrics going forward. Another part of this as well, of course, was the introduction of more flexible programming languages, where we basically see it becomes a lot easier basically to move your code over to GPU. You don't necessarily have to be an expert in CUDA for NVIDIA or HIP for AMD, which has allowed us to be able to really accelerate our progress in being able to use GPU hardware. And then one of the most important points is that across the board, really, we've seen very good performance from GPUs in terms of flops per watt, flops per dollar, and flops per meter squared. So for the same simulation throughput, you can use less energy, it can cost you less, and it can take up less physical space as well. So all of these factors are really helping drive GPU-accelerated CFD. And just to kind of quantify that, it's not a very scientific method, but I did have a quick look at journal articles referencing GPUs and CFD, and we can see a kind of steady increase up to 2017, where we saw the introduction of one of the kind of first HPC type GPUs that can really be used for real CFD problems, I would say, which was the V100. So by introducing 32 gigabytes of high bandwidth memory, then you were able to start to take on more industrial CFD problems with these cards. Moving a bit further forward, we start to see this increase continue, and that also ties in nicely with the introduction of the A100. So the A100 is the GPU we'll be talking about today and looking at today, and this was really, again, another step change in terms of performance. For example, with STAR-CCM Plus, we see roughly 2x performance increase, moving from a V100 to an A100. And likewise, with the introduction of even more memory per GPU card, then you can really start to look at bigger, more industrial problem sizes with these GPUs as well. So I don't think it's any surprise that with the A100, we then see a bit more of an explosion of GPU and CFD journal articles. And now coming towards 2023 and 2024, then the hardware continues to improve. So some examples here would be like the H100 from NVIDIA was released in 2023, has even more performance improvement, and likewise the H200, which was released this year, again has even more memory and more memory bandwidth. So you can start to really fit much bigger CFD problems onto your GPU cards, and this is really now making large-scale problems with really good performance a reality in the world of CFD as well. So specifically looking at Simcenter STAR-CCM Plus and our approach and current capabilities. So ultimately our objective here is to enable GPU acceleration of STAR-CCM Plus. The end goal there is for faster turnaround time of simulations as well as a lower per simulation cost. We typically look for a seamless experience. So we acknowledge, of course, that there's multiple different HPC architectures out there. Therefore, we want to be able to look at being able to run on GPUs, traditional x86 CPUs, ARM CPUs, and we have a tool that can basically run across the kind of range of different hardware types, which is great because if you go on to, for example, the VSC cluster, then you can use the available CPU nodes or the available GPU nodes. And the idea is that we have a seamless experience and we should have very similar solutions across all hardware types as well. When we talk about GPU acceleration, then what we mean is that basically all our core CFD solvers and all the compute intensive code is run directly on the GPU. So it's not like a partial offloading where some parts of the code are on the GPU, other parts are on the CPU. We typically, once we have physics models running on GPU or ported, let's say, to GPU, then all the heavy computational work is directly on the GPU. And that's really essential to maximize the performance benefit. If you introduce a lot of data migration between a CPU and a GPU, then that bottleneck can impact the performance. So we try and avoid that where possible. And as we move through our releases, then we'll further expand the native GPU support to other models and solvers. I'll give a kind of summary on the next couple of slides. But just talking about the seamless experience, then this is a nice example of an external aerodynamics case between a steady state RANs. And it's very hard to differentiate here basically any difference in solution between the CPU and the GPU as well. So yeah, you would be hard pressed to guess what one was what. Qualitatively here, then we have very close predictions between the GPU and the CPU solution, which is ideal. And quantitatively, looking at the pressure coefficient across the center line of the car, then again, we see very, very good agreement, almost no difference between the CPU and the GPU-based solutions. In terms of functionalities, so as of our current release in 2402, then there's already quite a wide range of applications that can leverage GPU hardware. So we've had some type of GPU functionality in the software for about 2 years now, so in our first 2022 release, and we've expanded the applications as we've moved through further releases. So in terms of what you can look at now, then things like unsteady vehicle aerodynamics, aeroacoustics, high fidelity large eddy simulations, things like combustion, steady aerodynamics with the coupled flow solver, hypersonics with real gas, and things like multi-timescale conjugate heat transfer with our mapped contact interfaces. So that there's really already quite a wide range of applications, and you can see some of the specific submodels as well. So we do try and keep an application focused approach, but in terms of individual models, you can see them at the bottom of the screen here. If you are interested in a comprehensive list, then that is in this STAR-CCM Plus documentation, or you can reach out to me afterwards, or one of your dedicated support engineers if you want to know the details about some other specific models as well. Okay, so moving on to some practical tips now for running Simcenter STAR-CCM Plus on GPUs. So how do we actually launch or invoke the usage of GPUs? So there's a few criteria that have to be satisfied in order to use GPU hardware, or can also commonly be referred to as GPU, which is a general purpose GPU as well. So the good news is that it's a single installation for STAR-CCM Plus, regardless of whether you look at CPU or GPU. So you do not have to have 2 different versions of the software installed. It's a single installation, and if you want to use GPUs, then you basically just have to add this option -GPU to the command line. So basically, one addition to the command line will start STAR-CCM Plus to look towards using the GPU hardware. One thing you have to be aware of is that you can only use the GPU compatible models and solvers for that simulation. So as I mentioned, we don't have a kind of hybrid approach currently. You either have to use fully GPU ready models, or you have to use CPUs at that point in time. And then the final part here is you have to have POD hours, so that's power on demand hours, or a Power Session Plus license to use GPU hardware. So the Power Session Plus license is very similar to the Power Session license, and basically it allows you to run on an unlimited number of GPUs or CPUs. So yeah, it doesn't matter if it's 1 GPU or 100, it's the same license type there. And it can be used for CPUs as well. So what happens if you don't kind of satisfy those criteria? So if you do try and select a model that is currently not ready for GPU, then you should see a warning sign in the output window. So an example here is Lagrangian multiphase. That's not currently ready for GPU. So you would see a warning message like this, and the simulation would revert to using CPUs instead. We do have an extra option if you're in batch mode. This can be especially useful for on the cluster. Then if you encounter this type of incompatibility, then the simulation will basically just automatically exit. So you're not holding up any cluster resource. So an example would be if you submitted a job onto a GPU node. If we take this example here, then Lagrangian simulation, then you could basically kind of gracefully exit and free back up the cluster resource using this require compatibility option on the command line. So I generally recommend that as a good practice to avoid holding up GPU nodes that aren't really using the GPUs correctly. So a little bit more detail, it's kind of a busy slide, but when we use the -gp-gpu command line, there's a few specific options that can be leveraged. So the first one here is auto, which is, I would say, the most standard, the one I use most often. And as it says here, that automatically uses all the available GPUs for the resources that you have requested. So again, if you are on the VSC supercomputer, you ask for 2 nodes of 4 GPU cards, and you use the auto option, then it will basically automatically use all 8 of the GPUs that are available to you. If you want to get a little bit more granular, then we do also have this option to specify the exact index of which GPU to use. So the example here, you could say, okay, I want to use GPUs 0 and 1, and that basically correlates to the indices reported by the NVIDIA SMI tool. So if you're on a GPU node, you can basically run this command, just run NVIDIA-SMI in your terminal, and you'll get an output that looks something a bit like this, which basically lists all of the available GPUs on that node. So the example we see on the screen is a node that contains actually 8 A100 cards, and you can see that it basically looks at the different indices of the GPU, and that basically relates back to what you can specify directly here. So in theory, I could ask it to run on GPUs 0, 1, 2, 3, and I could ask another job to run on GPU 4, 5, 6, 7 in this case, for example. The final option, if you're perhaps used to using machine files with STAR-CCM Plus on CPUs, we have the exact same option on GPU. So you can actually configure a machine file and pass that along, which would specify the GPUs to be used. Typically for best performance, we actually suggest to use 1 CPU process per GPU. So that's basically what I would call more of like a controller process. So it just manages some aspects of communication. There's nothing to stop you running on more CPU processes per GPU, but we see the best performance when you run with that kind of 1-to-1 ratio typically. So if we take all of that into consideration, then I would say a fairly standard batch command for launching a GPU run would be something like this. So -gp-gpu auto, CPU bind, GPU aware, which I'll come back to, and then -batch if you're running in batch on the cluster, and then specify the number of CPU processes here as well. So yeah, just to clarify, this flag will invoke the GPU usage and automatically use all GPUs. This CPU bind, GPU aware, will ensure that any CPU processes are placed on cores which are physically close to the GPU that's being driven, so ideally on the same node. And then the -MP4 here, so that should equal the number of processes that number should equal typically the number of GPUs that are being used. So If we talk about VSC, where there's 4 GPUs per node, then this command would be ideal for if you're running a job on a single GPU node. In terms of what actual GPUs we support currently, so we support the use of a single GPU card, multiple GPUs in a node, and multi-node GPU. So we'll see the example later, but you can run on anything from 1 card to, I don't know, 48 cards over 12 nodes, even further, if you have the cards available. In general, we do see better performance from cards with high bandwidth memory instead of GDDR memory, and most of the HPC resources typically have the cards with high bandwidth memory installed anyway. So for NVIDIA, we support GPUs with the Volta, Turing, Ampere Hopper, and Ada Lovelace architectures. So just some examples of what you might see in a workstation would be an RTX A6000 or an RTX 6000 Ada generation type card. And on HPC systems, we would see things like NVIDIA V100, maybe a little bit outdated now. The A100 is pretty much one of the standards for lots of GPU HPC resources, but also now starting to see more and more the H100 and H200 appear as well. We also support AMD GPUs with the CDNA architecture newer. So some examples at a workstation level would be Radeon Pro W6800. On HPC systems, then we support the Instinct MI200 or MI100 or MI200 series GPUs. And in the upcoming release in the summer, we'll also support the later generation now, the Instinct MI300 as well. So we work very closely with the hardware providers to make sure that we can run on the latest generations of GPU because they're basically introducing these on an annual basis now, it seems. So one aspect of GPU that you have to consider a bit more carefully compared to CPU is your available memory. So the trend is getting much better. So the later generations of cards have more memory, but still it can be a bit more of a precious resource on GPU compared to a typical CPU node. So if we just look at an example here, this is the A100, which is the card we'll be using later and for the kind of case study. And that comes in 2 different configurations. So it can have 40 gigabytes of memory or 80 gigabytes of memory. And you can see here roughly the maximum problem size that can be fitted on a single GPU card. And that's basically dependent on your mesh type and also dependent on whether you are using the segregated or coupled flow solver as well. So if we just take, for example, trimmed mesh is what we're going to be looking at today, then if we look at the 80 gigabyte configuration, then you could fit up to 64 million cells estimated for the segregated flow problem, and for the coupled flow, which is more memory intensive, which is the same on CPU, then we can fit about half that, so 32 million cells per card here. And then similarly for polyhedral meshes are a bit more memory intensive and therefore can fit slightly less cells per card. The good news, of course, is this isn't a hard limit. As I said, we can run on multiple cards. So if you have in fact, one of the examples I'll show today is a 320 million cell mesh. So we just have to run over more cards to basically fit that problem. So it's not really an issue. If you have a kind of typical HPC configuration where you might have at least 4 cards per node, then effectively you can multiply this row by 4, and that would be the problem size you could fit per node. So you can already start to expand into larger problem sizes as well. You can track all of this as well inside your simulation. So inside Simcenter STAR-CCM Plus, we've always had the option to create a memory report where you can track the memory consumption. And we also then added the option to specifically track the GPU memory that's being used. So If you are running a job on GPUs and you're kind of curious to build a similar table to what was on the screen for your specific problems, you know, as I said, this was a 2-equation turbulence model flow simulation, but if you're looking at, I don't know, something like combustion, you might have slightly different values, then you can always use the maximum memory report here to track the memory consumption as well. So in terms of maximizing performance, then as I mentioned, in general, we see the best results with one CPU process per GPU card. So that would be our kind of recommendation as a starting point. Another kind of interesting thing about GPUs is, you know, as I say here, utilize them. So the most efficient performance for a GPU is when it's really maxed out. So you're, in a sense, fitting as many cells as possible onto that single card. That's what gives the most efficient performance. And typically we can maintain close to linear scaling if we use at least 30 to 50% of the GPU memory. If there's too few cells per GPU, then effectively there's just not enough work for the cards to do. And this is kind of analogous to running a very small flow problem on thousands of CPU cores. It's the same idea with GPUs, except an individual GPU card typically has a lot more processing power than one CPU core. Therefore, the rules are slightly different. So as I say here, a rule of thumb, so like a rough estimate, we see in and around 5 million cells per card can give quite good scaling. Obviously that can vary, but again, it's quite a good kind of starting point if you want to maximize or use the GPU in an efficient manner. Then I would say try and have at least 5 million cells per card. And then you can go upwards from there to the kind of upper limits of the memory per card. In terms of post-processing, then it's not just about physics models. We want to make sure that full simulation process is native to the GPU, again, to avoid any data migration. So most of these standard monitoring, so standard field functions, user-defined field functions, if you're monitoring those values on regions or boundaries, or also parts and surfaces in terms of the specific STAR-CCM plus terminology, then that's all directly monitored on GPU, which is good. So we don't see any kind of performance impact there. Likewise, if you're running a transient simulation, then all of the calculation of mean data, so things like field means or field variances, to get your kind of averaged fields, then that's also all directly calculated on GPU. So again, we don't see any kind of performance impact there. A few areas we're still working on, which might be kind of a point of caution. So as it stands today, monitoring of values on plane sections and probes, so point probes or line probes, that's currently on the CPU. So that may impact performance when you have lots of monitors being used. So if you have, I don't know, hundreds of probe points or tens of plane sections being monitored, then that can kind of impact a cost on the GPU. The good news is that actually having that calculation directly on GPU will be introduced from version 2406 in the summer. Then another thing to be cautious of is if you do, maybe slightly less common, but if you do monitor values directly on ISO surfaces and thresholds whilst the simulation is calculating, then that is also currently on CPU, and it's something we were looking to address. So basically, if you have lots of these type of monitors, I would see if there's a way to kind of maybe avoid that when you're using GPU hardware, just to maximize performance currently. But as I said, we are working on removing that kind of limitation as it stands. Okay, so that was a lot of background. Let's look at a practical example now. So I want to say thank you to Jan and Carl and the team at VSC. They gave us some access to the Hortense Tier 1 supercomputer, so we were able to run some tests on the available nodes there. Obviously, I would just like to add that these are indicative results. we would obviously recommend to test your own simulation files as well, before you dive straight in. But again, they show at least a good kind of direction here on the potential benefits of GPU as well. So a little bit of background on the actual simulation we looked at here. So this was an automotive external aerodynamics case. We have 3 different meshes, so 57 million, 106 million, and 322 million. The domain has 5 fluid regions or 1 porous region. We do look at the segregated and coupled flow solvers here. The coupled flow solver is using the auto CFL functionality. Segregated flow solver is just, as it says here, is using standard flex cycle and V cycle for velocity and pressure. We use the SST turbulence model, and the iteration times calculated here have been calculated using the inbuilt benchmarking option, so the dash benchmark option in the command line, and we've averaged over 20 sample iterations here from a converged solution, I should say. And for this case, all the tests were conducted using Simcenter STAR-CCM plus 20D10, so that was our previous October release as well, and it was a mixed precision version, I should say. So in terms of what partitions we tested, so I just grabbed this off of the VSC website. You can see here that there's basically 2 main CPU partitions that have the AMD Rome CPUs and the AMD Milan CPUs, and likewise there are 2 GPU partitions. Both have the NVIDIA A100. However, one set has the 40 gigabytes of memory and the other set has the larger 80 gigabytes of memory as well. So we ran simulations across all of these partitions, and we'll show the results here. So the first thing I wanted to look at was weak scaling. I've called this weak-ish scaling. The idea behind weak scaling is that we take a simulation. So in this case, we take the 57 million cell problem. We run that on 4 GPUs. We then roughly double the mesh size and run on double the number of GPUs. And then after that, we actually we tripled the mesh size and run on triple the number of GPUs. So it wasn't exactly the same, but the objective here is to have the same number of cells per single GPU card. And ideally, we want to see a flat line here. So basically, as we increase the problem size, but we also increase the number of GPUs, then we should see roughly the same time to solution. For the most part, we do look in quite good shape here. I've not had enough time, to be honest, to deep dive into the 106 million cell case, which does seem to kind of consistently jump off the page or off the kind of linear or ideal lining. But off the top of my head, it might be slightly different auto CFL performance, so that might be introducing some more AMG cycles per iteration, which could be skewing the numbers here slightly. But overall, actually, if we compare the 57 million through to the 322 million, then we actually have pretty good weak scaling performance. And you can see we're fairly consistent with the number of cells per GPU, so 14 million and then 13 million roughly for the second 2 cases. And likewise, there's not too much difference between the 40 gigabyte A100 and the 80 gigabyte A100 as well. A fairly constant offset, which isn't surprising since there's slightly better performance from the 80 gig GPUs. In terms of strong scaling, so now we just take these simulations and we run them on an increasing number of GPUs to compare. So we have 3 different aspects here. Maybe if I just add I thought I could add my pointer, but maybe not. If we look at the 57 million cell case, then we can see again, for the 80 gigabytes, we can actually run this case on only at least 2 GPUs for the coupled flow. And then for the 40 gigabytes, we have to run on 4 GPUs just because of the less available memory. But overall, we see pretty good, strong scaling performance. And likewise for the 106 million cell case and the 322 million cell case, we see pretty good scaling here. And to go back to that rule of thumb, where we start to see the deviation from the ideal scaling is when we start to have too few cells per GPU. So here we start to move towards 4 million cells per GPU or 3 million cells per GPU. So we start to kind of move away from the linear kind of scaling here as well. For the larger case, I didn't have the opportunity to run on even more GPUs. Maybe it's something to test after this. But you can see we're at the 7 million cells per GPU range here, and we're still maintaining pretty much linear scaling for this case, which kind of ties in with the general rules that we had observed previously. Okay, now moving on to compare to the CPU compute nodes. So we now have the A100s in the kind of blue colors here, and then the red are the CPU nodes with the Milan instances, and the green is the older generation Rome instances. So again, this is the 57 million cell case coupled versus segregated flow. And the interesting point to clarify here is here we're looking at the individual number of GPUs, but for the CPUs, we're actually looking at the number of nodes, which correlates to the number of cores above here. So we can already see, like this is just taking both simulations and running them kind of out the box, let's say, but we can actually see straight away that even 2 GPU cards is performing, you know, almost let's say roughly the same as 4 nodes of CPUs here. So, you know, let's say 512 cores. So basically that's half a node already really performing at a very high level in terms of time per iteration. I should point out this is a log scale. So we see really quite nice performance, and that trend continues. In fact, for this case, we start to see the scalability of the CPU drop off a bit faster than the GPU. And you can really drive to even faster absolute time to solution as well with the GPU nodes here. So we can see some examples as the CPU scaling starts to drop off, then this kind of gap widens even further. So here we're seeing that 16 GPUs, so 4 nodes, is actually in this case 3 times faster than 16 nodes of CPUs. So quite a substantial potential here for performance improvement. And again, this is one of the big drivers of why we are really trying to make sure that we can run STAR-CCM Plus on this type of hardware, because the potential benefits are really quite high. You know, likewise, pretty similar story for the segregated flow solver. In fact, we see even a slightly bigger gap, and that's kind of holds in general. We do tend to see that segregated performance on GPU relative to CPU is even better than the coupled flow performance as well. So something else I tried was to estimate the energy consumption. This is, I should say, is just an estimate. This isn't any directly recorded energy consumption, but just to give a feel. We can look at the thermal design power of a GPU node. So for the 80 gig configuration, then we have 4 GPUs with 400 watts each. We have actually got the 2 CPU cards in there as well. So that gives you a total of roughly 2000 watts per node. For a CPU, then we have, as it says here, 2 of the 64-core AMD EPYCs, and that's given us 560 watts per node. As we saw on the previous slide, the GPU runs faster and requires less nodes. So for the same actual time to solution, we can estimate the energy consumption. So we should have roughly the same wall clock time, but the CPU the CPU requires 16 nodes, whereas the GPU only requires 1 node. So even though this number is higher, we need less of them compared to CPU. And basically translating that into an energy consumption estimate, then we can say that for the same time to solution, the GPU node is using less than 20% of the energy for the same time to solution. So As I said, this is a kind of rough estimate, but overall, it gives a good indicator of the potential here for GPUs to also save on energy whilst running your simulations. Just a follow-up example on the larger mesh sizes, but again, it's a very similar story. So here we can run the 106 million cell case on 4 of the 80 gig A100s or 8 of the 40 gig. And again, we see much faster time to solution here, both in terms of the fact that you can really drive the absolute time much lower, but the fact that a single GPU node of 4 cards is almost 2 times faster than 4 CPU nodes as well. So really, again, very nice performance here from leveraging the GPU nodes. And likewise for the largest case we tested, so that's 322 million cells, then that can fit on 12 GPU cards for the 80 gig. But in general, we can even run upwards to 48 cards here. We get the CPUs are already kind of flatlining in terms of scalability, and we could really drive the time to solution down quite significantly. So I think one of the main takeaways here is that if you have physics applications that can run on these GPU nodes on Hortense, then I would definitely recommend to try and take advantage of that, because you can really drive down the time to solution here quite substantially. And just a final quick example, because I had some time, I ran a wall-modeled LES case, which was 130 million cells, 5 inner iterations per time step with segregated flow. And once again, it tells a similar story. The GPUs are performing really quite well here. We do actually see very good scaling on this case for the CPUs as well. But yeah, again, the GPUs can offer a much faster time to solution. If we kind of scale this out to, for example, 4 seconds of physical time, so an actual real simulation, then on the CPU nodes, this could take, let's say, if you use 16 CPU nodes, it can take 13 hours. If we use the GPU nodes, we can really drive this turnaround time down quite substantially. So, for example, here, if we use 16 GPU cards, which is 4 nodes, then we can already run in 7 hours. If you go out to 8 nodes, you're down to 5 hours. So practically, you can run 4 or 5 of these LES simulations in a day, which is quite substantial, and a really nice opportunity to basically use GPUs to drive towards more high fidelity applications as well. Okay, so as we kind of move to final thoughts and looking forward, what's in store? So as I said, the hardware continues to get better. This was some analysis that was done with STAR-CCM Plus by NVIDIA. And you can see, so today we're talked a lot about A100s, but I mentioned the H100 and the recent H200. There's increased memory bandwidth, more than 2 times the memory bandwidth going from the A100 to the H200. And we see that in the performance of STAR-CCM Plus. So in this case, it was a 115 million cell coupled flow problem on 8 GPU cards. And you can see the performance improvement of STAR-CCM Plus ties in quite nicely with the increase in memory bandwidth. So yeah, we expect as the hardware continues to improve, then you'll continue to see improvements for CFD applications like STAR-CCM Plus as well. And what's in store for us? So, one big part of this is we want to be able to model or take advantage of this across a wide range of physics. I did demonstrate quite a lot of applications that are already available on GPU, but our objective is to leverage the fact that STAR-CCM Plus is a multi-physics tool and look at where we can take the advantages we've already seen and extend them across a wide range of physics. So our SPH solver, discrete element methods, multi-phase flows, things like radiation are all on the agenda for GPU native functionality as well. So I think this is my last slide. basically I wanted to point out, so we are production ready, so we do have a wide range of applications that can leverage GPUs today. I just looked at one case there of automotive aerodynamics, but as I showed, we can do things like combustion, hypersonics, turbo machinery, lots of different applications, lots of potential for cost and energy savings. That kind of simple calculation I did today was showing the potential of up to 5 times the energy reduction. So we can really use GPUs to deliver on cost and energy efficiencies that are required, or for the same amount of simulations, for the same level of cost and energy, you can really increase the number of simulations that you can run. Go faster. So with the example we shared today, we can see that even a single GPU node of 4 cards can give turnaround times equivalent to many multiples of CPU nodes, which again is another potential for a really good benefit there. And finally, consistency. So Simcenter STAR-CCM Plus is hardware agnostic. We see lots of applications that will still require CPUs in the near future. Things like fluid structure interaction, adaptive mesh refinement, those physics models we don't have ready yet. But we also have the power to run on these GPU nodes as well. So, as I said here, if you've got the CPU nodes available or the GPU nodes available, then yeah,